The adrenal hormones are central to the body's response to exercise stress, especially in high-intensity situations like strength training or endurance events. The adrenal gland, located on top of the kidneys, plays a vital role in the body's fight or flight response. It is divided into two main parts: the adrenal medulla at the center and the adrenal cortex, which surrounds the medulla like a shell. Both of these divisions respond to exercise but do so in different ways. The adrenal medulla is directly stimulated by the nervous system, making its response nearly immediate. In contrast, the adrenal cortex is stimulated by adrenocorticotropic hormone, which is released from the anterior pituitary gland. The adrenal hormones most critical for training and conditioning include cortisol, which is a glucocorticoid produced by the adrenal cortex, and the catecholamines, epinephrine, norepinephrine, and dopamine produced by the adrenal medulla. Cortisol is often labeled as a catabolic hormone because it plays a role in breaking down proteins in the body. However, its role is more complex than simply being catabolic. Cortisol is the primary signal for carbohydrate metabolism and is linked to the body's glycogen stores in the muscles. When glycogen levels are low, cortisol signals the body to break down proteins to produce glucose, ensuring that blood sugar levels remain stable during exercise. Cortisol follows a natural circadian rhythm, with levels peaking in the early morning and gradually declining throughout the day. This rhythm is essential to consider when measuring cortisol levels, as the time of day can significantly impact the results. Cortisol exerts its catabolic effects by converting amino acids into glucose, increasing the activity of proteolytic enzymes that break down proteins, inhibiting protein synthesis, and suppressing glucose-dependent processes like glycogenesis and immune cell function. The effects of cortisol are particularly pronounced in type 2 muscle fibers, which contain more protein than type 1 fibers and are more susceptible to cortisol's protein-degrading effects. In contrast, type 1 fibers rely more on preventing protein degradation to promote hypertrophy, while type 2 fibers experience muscle growth through increased protein synthesis. In cases of illness, injury, or muscle disuse, elevated cortisol levels can lead to muscle atrophy and a decrease in force production. However, the catabolic effects of cortisol in muscle tissue are counteracted by the anabolic effects of testosterone and insulin. If testosterone binds to more receptors than cortisol, protein is preserved or even enhanced. However, if cortisol dominates, protein breakdown occurs, leading to muscle loss. Thus, the balance between anabolic and catabolic activity in the muscle directly affects the protein contractile unit, which in turn influences strength. In fact, cortisol plays an important role in the tissue remodeling process after exercise, as its presence helps remove damaged proteins and may assist in the recovery process. Resistance exercise significantly affects cortisol levels. Like growth hormone, cortisol levels tend to rise with resistance exercise, especially when rest periods are short and the total volume of work is high. However, these short-term increases in cortisol may not be harmful and could be part of the muscle remodeling process that follows intense exercise. While chronic high levels of cortisol can be detrimental, leading to overtraining or muscle wasting, acute increases in cortisol may play a role in muscle adaptation by helping to remove damaged proteins. Cortisol has also been studied as a potential marker for tissue breakdown during exercise. Many athletes and strength professionals look at cortisol as a whole body marker to gauge potential overtraining. Some research suggests that an increase in cortisol greater than 800 nanomoles per liter may indicate overtraining. The testosterone to cortisol ratio has also been examined as a potential marker of anabolic and catabolic balance in the body. However, using cortisol as a predictor of strength or power changes has had limited success due to the hormone's multiple roles in the body. Interestingly, resistance exercise exercise seems to affect glucocorticoid receptors in muscle tissue differently for men and women. Research has shown that trained men have significantly lower concentrations of glucocorticoid receptors at rest and during recovery than women. Additionally, women show a faster upregulation of androgen receptors after exercise, which could explain why women seem to handle cortisol's catabolic effects better than men in some cases. Cortisol plays an essential role not only in muscle metabolism but also in the immune system. After intense exercise, cortisol suppresses the activity of immune cells, which contributes to the immune suppression often observed after heavy exercise. This suppression is part of the body's response to exercise stress, helping to allocate energy and resources toward muscle recovery. However, if cortisol levels remain chronically elevated, it can hinder the recovery process, leading to muscle atrophy and immune dysfunction. Alongside cortisol, the catecholamines, primarily epinephrine, but also norepinephrine and dopamine, are produced by the adrenal medulla and play a key role in exercise. These hormones are critical for the acute expression of strength and power, as they act as central stimulators for the nervous system, increase muscle contraction rates, and enhance metabolic enzyme activity. Epinephrine and norepinephrine are part of the classic fight or flight response and increase blood pressure, energy availability, and blood flow to the muscles during intense exercise. Catecholamines are closely tied to resistance exercise, as research has shown that men who experienced a higher release of catecholamines during a heavy resistance session were better able to maintain force output throughout the workout. Although catecholamines are not directly associated with muscle growth, they help stimulate other anabolic hormones like testosterone, which promote hypertrophy. During exercise, catecholamines are responsible for several physiological changes, including increased force production, enhanced metabolic enzyme activity, and increased availability of energy through glycogen breakdown and fat mobilization. They also increase muscle blood flow and enhance the secretion of other hormones. For example, epinephrine has been correlated with lactate concentrations during exercise stress, indicating its role in regulating energy availability during intense workouts. Training adaptations for catecholamines show that athletes who engage in heavy resistance training can increase their ability to secrete more epinephrine during maximal exercise. Over time, this allows for better force production and improved metabolic control during exercise. However, it's important to vary training protocols to allow the adrenal glands time to recover. If the adrenal glands are constantly stressed by intense exercise, recovery may be delayed, leading to overtraining and adrenal exhaustion. The adrenal hormones, particularly cortisol and catecholamines, play crucial roles in responding to the physical stress of resistance exercise. Both acute and chronic responses to these hormones must be managed carefully in training programs to optimize the performance and recovery while avoiding overtraining. These hormones are essential in the body's adaptive processes and are key components in the physiological changes that occur during and after resistance training. In summary, cortisol and catecholamines are critical components of the body's response to stress, including exercise. While cortisol is often viewed as catabolic, its role in the body is much more nuanced, as it helps with carbohydrate metabolism, protein breakdown, and tissue remodeling. Catecholamines, on the other hand, are vital for immediate physical responses to exercise, helping to increase force production, energy availability, and muscle contraction rates. Both hormones play a vital role in the overall hormonal response to resistance exercise and are key factors in the body's ability to adapt to training.